Identify patterns. Classify data. As humans, we constantly categorize our surroundings. We organize our Microsoft Word documents into specific folders, distinguish between business and personal contacts, and alphabetize lists. These classifications help us manage data efficiently. Similarly, businesses need to organize their data. Airlines categorize customers based on their frequent flyer status, retailers identify their highest spenders, and search engines predict your online purchasing behavior. Binary classification, a widely used supervised machine learning technique, simplifies this process by offering two possible outcomes. For example, will a hotel room be booked next week? Will the stock market rise this afternoon? Is an email spam? Binary classification relies on labeled data, training the system to distinguish between two answers. Credit card fraud detection exemplifies binary classification. Every transaction is classified as either fraudulent or legitimate using machine learning algorithms trained on thousands of labeled examples. Similarly, email providers filter spam by training algorithms with pre-labeled spam messages. This method involves processing vast amounts of data to categorize it into meaningful groups like booking data, fraudulent transactions, or unwanted emails. Data scientists define these categories and train AI systems to recognize them. Though popular, classification requires significant upfront effort to gather and label enough data to train the system accurately. For instance, identifying tens of thousands of fraudulent transactions or spam emails can be challenging, and there's no assurance that this volume will suffice for precise predictions. Consequently, data science teams might need to collect more data to enhance the system's accuracy. Despite years of development, you might still receive false fraud alerts from your credit card company. Data scientists continually refine these systems to improve classification accuracy. Whether it's fraud detection, spam filtering, or predicting online purchases, machine learning systems approach these tasks by classifying labeled data into predefined categories. Cluster data. Classifying data isn't always the best approach for every problem. For one, the system may not always have access to large amounts of labeled data. In such cases, it can be beneficial to allow the system to create its own clusters of data. Clustering involves using unsupervised learning to form groups based on patterns found in the data itself. For instance, when you shop online, you might see recommendations like frequently bought together, such as suggesting a keyboard when you buy a mouse. This feature helps customers discover products and boost sales for the company. It exemplifies unsupervised learning at work, where clusters are formed based on purchasing patterns rather than predefined categories. The main distinction between clustering and classifying lies in the source of the categories: human-defined for classifying, supervised learning, and machine-defined for clustering, unsupervised learning. To illustrate, think of Halloween. My son goes trick-or-treating and returns with a variety of candies. He wants to sort them based on his preferences. And with my guidance, leveraging my experience, he can classify the candies into categories like chocolate, peanut butter, mints, and gummies. This mirrors supervised learning. However, his grandparents from another country send a bag of Serbian candy each year, which we've never seen before and is unlabeled. Here, he uses unsupervised learning to create clusters based on size, color, or even unique traits like a perfume candy cluster made from rose and orange blossom flavors. This self-created categorization is akin to clustering in machine learning, where the system identifies patterns and forms groups independently. Clustering is particularly advantageous because there is an abundance of unlabeled data. There are many candies I've never seen, making it difficult to create predefined categories. Similarly, machine learning can be used to cluster customers, allowing humans to identify patterns and insights from these clusters. Although these clusters may initially seem trivial, they can be incredibly valuable. Major companies like Amazon, Netflix, and Twitter leverage clustering to analyze your social connections, search history, and buying behaviors, uncovering patterns that humans might miss. Reinforcement learning. The online music industry, valued at nearly $30 billion, presents an intriguing business model. With access to the same tracks on platforms like Apple Music, Spotify, or Tidal, why do users choose one service over another? A major factor is the strength of their recommendation systems. Initially, many of these systems relied on unsupervised machine learning, recommending songs based on patterns similar to how online retailers suggest frequently bought together items. However, top-tier music libraries aim to help users discover new music, requiring a more advanced approach. Reinforcement learning, RL. RL algorithms use rewards to incentivize the system to identify new patterns. Google famously used RL to train AI systems to master video games, outperforming expert players in classics like Pong and more modern games. Beyond gaming, RL can continuously improve through goal setting and rewards. Take Spotify's Discover Weekly as an example. It compares your favorite songs with similar tracks, tracking your interactions. Each click and the duration of your listening contribute to a digital reward system designed by data scientists. The algorithm receives a tiny reward every time you click on a recommended song, with additional rewards for longer listening times. One specific RL technique, Q-learning, uses rewards to enhance outcomes. In Q-learning, the algorithm starts with a baseline reward, Q, of 0. Through interactions, the system learns which actions improve its state, incrementing its Q value with each positive outcome, akin to accumulating coins in a bank account. As the reward system evolves, it detects patterns, such as users who enjoy one song often liking another, and leverages this to refine recommendations on Discover Weekly. Reinforcement learning excels in scenarios where organizations seek to foster discovery beyond basic item clustering. With RL, businesses can develop systems that creatively predict and enhance customer experiences. Machine learning algorithms. Machine learning stands out as a leading area in artificial intelligence, largely due to the massive influx of data and significant advancements in machine learning algorithms. Essentially, machine learning consists of various techniques for developing systems that learn from data, surpassing the need for explicit programming inherent in early AI systems. Instead of one comprehensive machine learning program, there are numerous algorithms, many of which originate from statistics. Think of these algorithms as different tools in a chef's kitchen, each serving a distinct purpose but also adaptable for creative uses. For example, a knife can both chop vegetables and crush garlic. In a company where I previously worked, we used credit card data to develop customer promotions. Initially, we employed supervised machine learning for binary classification, sorting customers into those who used promotions and those who did not. With this foundation, we then applied unsupervised machine learning to identify patterns within the promotion using customers, discovering a subgroup that consistently used promotions, dubbed the promotion super users. This insight allowed the company to refine their strategy, targeting these super users with more promotions, which significantly improved their success rate. Understanding machine learning requires recognizing that different algorithms excel in either supervised or unsupervised learning contexts, each with unique strengths and weaknesses. Some demand substantial processing power, while others are more efficient but less precise. Despite these distinctions, a skilled data science team can creatively combine these algorithms to extract the most valuable insights from their data. Most machine learning software toolkits include these algorithms, enabling data science teams to leverage their expertise and creativity effectively. K-nearest neighbor. In machine learning, understanding your data often starts with classifying it based on known categories. Let me illustrate this with an example. When I was younger, I volunteered at an animal shelter in Chicago. One of our challenging tasks was identifying the breed of each incoming dog. With hundreds of breeds and many mixed breeds, we would compare new arrivals to dogs whose breeds we already knew, focusing on specific features like facial shape or hair color. Essentially, we were classifying the unknown dogs by comparing them to the nearest known examples. Similar to how the K-nearest neighbor, KNN, algorithm works in machine learning. KNN is a popular supervised learning algorithm for multi-class classification, where it plots new data points and compares them to existing ones, aiming to minimize the distance between them. This distance can be measured using methods like Euclidean distance, which helps determine how closely features match. Imagine you have millions of dogs to classify by breed. You might start with two key features, such as weight and hair length, as classification predictors. By plotting these features on an XY axis, with hair length on the Y-axis and weight on the X-axis, you create a visual representation of your data. Using a training set of 1,000 labeled dogs, you place them on the graph according to these features. Now, when you receive an unknown dog, you can plot it on the same graph. If you set K to 5, you draw a circle around the unknown dog and its 5 closest neighbors. Suppose 3 of these neighbors are shepherds and 2 are huskies. You can then reasonably classify the unknown dog as a shepherd, with a smaller chance it might be a husky. KNN is powerful because it extends beyond classifying dogs. It's widely used in finance to identify top-performing stocks and predict future trends, showcasing its versatility and effectiveness in various applications. K-means clustering. Another widely used machine learning algorithm is K-means clustering, which is an unsupervised technique for creating clusters based on the inherent patterns found in data. Consider an animal shelter in Chicago where dogs socialize in a large common area. Each social session, the dogs naturally form groups based on their friendships. Now, imagine the shelter is closing and the dogs need to be distributed to 3 new locations. To ease this transition, the organizers decide to group the dogs according to their social circles, forming 3 clusters. Here, the K in K-means is 3, representing the number of desired clusters. To start, 3 dogs are randomly chosen and given red, yellow, or blue collars, each representing a cluster centroid. The algorithm measures the average distance from each centroid dog to all other dogs and assigns the same colored collar to the dogs nearest to each centroid. Since the initial centroids are selected randomly, they may not form optimal clusters at first. For instance, if the centroid dogs belong to the same social group, most other dogs will be far from their assigned centroid. The algorithm then adjusts the centroids iteratively until it finds a configuration that minimizes the variance within each cluster. This process may involve multiple adjustments until stable clusters are formed. It's important to note that the algorithm simplifies the social dynamics into 3 clusters, even if the dogs naturally form more groups. Additionally, some dogs might interact with multiple groups, complicating the clustering process. K-means can also be sensitive to outliers, meaning a less social dog will still be forced into one of the clusters. Although organizing dogs into clusters for different shelters might not be a common problem, K-means clustering is extensively used in various fields. For example, retailers utilize clustering to segment customers into groups such as loyal customers, regular shoppers, and bargain hunters. They then devise strategies to convert regular shoppers into loyal customers. By clustering customers based on numerous variables, businesses can tailor their marketing efforts more effectively, showcasing the versatility and importance of K-means clustering in data analysis. Regression. I previously worked at a company that specialized in selling vehicles online, earning referral fees whenever a customer was directed to an auto dealership. The company closely monitored auto sales trends to optimize their seasonal promotions. They noticed that convertibles and sports cars were popular in spring and summer, while trucks and SUVs saw higher sales in fall and winter. To capitalize on these trends, they used regression analysis, a machine learning technique that examines the relationship between different variables and outcomes. In simple terms, regression analysis helps identify patterns and trends by analyzing historical data. For example, by plotting months against vehicle sales on a graph, they could observe trends such as an increase in convertible sales during warmer months and a rise in truck and SUV sales during colder months. Regression analysis doesn't explain why these trends occur but provides valuable insights into future patterns. The company used this information to align their promotions with customer buying behavior. Similarly, large retailers like Walmart leverage regression to stock products according to changing consumer preferences, ensuring that their shelves are stocked with items like Pop-Tarts in summer and dairy products in winter. While some debate whether regression qualifies as true machine learning, its predictive power is undeniable. If you're not leveraging regression analysis, you might be missing out on critical insights that could enhance your business strategy. Consider how regression could reveal trends in your own operations. It could be more revealing than you expect. Naive Bayes. In the realm of data classification, while methods like nearest neighbor or trend analysis can be effective, sometimes you need a more nuanced approach that considers multiple features simultaneously. This is where naive Bayes comes in. Naive Bayes is a widely used machine learning algorithm known for its simplicity and effectiveness. Its naive aspect stems from the assumption that all predictors are independent of each other. To illustrate, imagine we're using naive Bayes to classify dog breeds at a shelter. Suppose we define 3 breed categories: terriers, hounds, and sport dogs. For each breed, we will use 3 features: hair length, height, and weight. Although these features are not perfectly independent, for example, taller dogs tend to weigh more, naive Bayes treats each feature in isolation when making predictions. The algorithm computes the probability of a dog belonging to each breed based on each feature independently. For instance, it might determine that a dog with a certain hair length has a 40% chance of being a terrier, a 10% chance of being a hound, and a 50% chance of being a sport dog. It then does the same for height and weight, combining these probabilities to make an overall classification. By doing so, naive Bayes can effectively handle a large number of features, making it valuable for various applications beyond dog breed classification. For instance, financial institutions use it to detect fraudulent transactions by evaluating each predictor separately, and cybersecurity firms apply it to identify potential threats. Its ability to manage numerous predictors with minimal assumptions makes naive Bayes a powerful tool for data classification tasks. Fit the algorithm. Select the best algorithm. Now that we've explored 3 key supervised machine learning algorithms, k-nearest neighbors, regression analysis, and naive Bayes, alongside k-means clustering for unsupervised learning, it's important to understand how to best utilize these tools. Think of these algorithms like different kitchen utensils. Each is crafted for specific tasks, but with a little creativity, you can use them in various ways. Just as a chef might use a fork to whisk eggs or a knife to pit an avocado, data scientists often use multiple algorithms to achieve the best results. In the world of machine learning, this approach is known as ensemble modeling. Much like an ensemble cast in theater or music, where multiple performers come together to create a richer performance, ensemble modeling combines the strengths of different algorithms to enhance predictions. 2 popular ensemble methods are bagging and stacking. Bagging involves using multiple instances of the same algorithm to improve accuracy, while stacking combines various algorithms to leverage their unique strengths. For example, at a large home improvement retailer I once worked with, they faced a challenge in determining which items to place near the checkout to maximize sales. They experimented with ensemble techniques to find the most effective strategy. By using bagging, they tested different versions of the same algorithm, such as k-nearest neighbors, across various store locations to identify purchase patterns. Alternatively, they explored boosting methods to refine their predictions, starting with popular items like hammers and analyzing associated products, such as nails and tool belts. They also considered using naive Bayes to uncover less obvious correlations, like the surprising possibility that hammer buyers might also purchase chocolate bars. The key takeaway is that combining and experimenting with different machine learning algorithms can yield diverse and insightful results. Just as in any ensemble performance, the effectiveness of your predictions depends on the innovation and expertise of your data science team. Follow the data. In the classic film, All the President's Men, a crucial informant in the Nixon scandal advised, "Follow the money," to uncover the truth. Similarly, in machine learning, the key to discovering accurate insights lies in following the data. However, this process is fraught with challenges, particularly when it comes to managing bias and variance. Bias refers to the difference between the predicted values and the actual results. For instance, if you consistently predict rolling a5 with dice but roll a 4 instead, your predictions exhibit high bias. Variance, on the other hand, deals with the spread of the predicted values. If your predictions are scattered widely around different outcomes, such as predicting 5 but rolling 2, 4, and 6, you're dealing with high variance. Consider the analogy of a dartboard. If the darts consistently land in the same spot but away from the bullseye, you have high bias and low variance. The system is consistently off target but not spread out. To improve, adjustments need to bring the darts closer to the bullseye. Conversely, if the darts are scattered across the board, the system faces high variance. Here, the goal is to concentrate the darts around the bullseye to reduce variance. Ideally, You want predictions with both low bias and low variance, where all darts hit the bullseye. However, achieving this balance is complex. The bias-variance trade-off describes this challenge. Improving one often worsens the other. As such, machine learning algorithms must continuously adjust and optimize to find the best compromise between bias and variance, ensuring the most accurate predictions. Overfitting and underfitting. When my son was 3, we established a bedtime routine that included brushing his teeth, flossing, and taking a shower. One day, I received a call from his preschool saying he refused to nap unless they provided him with a shower, toothbrush, and flosser. I explained that it was okay to skip those routines for nap time, which made him visibly frustrated, but he eventually accepted. It became clear that the simple rules we had set at home didn't fit well outside our routine, so we adjusted them to add more flexibility. We made exceptions for naps at preschool, visits to grandparents, or flights. Each new exception seemed to add complexity, which my son found increasingly bothersome. This is similar to a problem in supervised machine learning. A system might create simple rules based on its training data, but these rules may not work well with more complex test data. Just as my son's rules needed to be adapted for different situations, machine learning models need to find a balance between simplicity and complexity. If a model is too simple, it may underfit the data, missing important patterns. Conversely, if it becomes too complex, it may overfit the data, learning noise rather than useful signals. For instance, if you work for a company like Zillow estimating home values, using just a few predictors like square footage, location, bathrooms, and bedrooms might be too simplistic, leading to underfitting. Housing data is varied, with many homes sharing similar features but differing in price. To improve accuracy, more predictors might be added, such as quality of view or modern amenities, increasing the complexity of the model. This could lead to overfitting, where the model becomes too tailored to the training data and struggles with new, unseen data. The key is to find a balance, ensuring the model is complex enough to capture relevant patterns but not so complex that it becomes unreliable.
Drop